In this lesson, amongst other things, we are going to be looking at the derivative of inverse trigonometric functions. On page 2 of the notes, you will see the same graphs that you see here. Now, we know that the sine of x traditionally continues. But what we need to do is restrict the domain of this function in effort that its inverse is also a function, such that this needs to pass the horizontal line test, so to speak, an effort for the inverse to also be a function. So what I'd like to do just quickly here is talk about what we need to restrict the domain. Here we need to restrict the domain to be between negative pi over 2 to positive pi over 2, including. The corresponding range will be from -1 to 1. If we do in fact restrict the domain as we see here, then the inverse will also be a function. So now let's take a look at the inverse function. The domain of this becomes -1 to 1. You will see that these flip-flop, and the range becomes from -pi over 2 to pi over 2. But what I am really most interested in is the derivative of this inverse function. So the derivative, take a look at this function and tell me, what do you notice about the derivative? Take a moment, think about it. Are you thinking that the derivative is always positive? If you are pretty much correct. The derivative is always positive between -1 and 1, not including the -1 and 1. We see that this function is always increasing, which tells me that the derivative is always positive. The exceptions are going to be at these endpoints where the slope is actually approaching positive or negative, approaching just positive infinity. So underneath here, I want to write that dy dx is greater than 0 on -1 to 1. And we can see that from the graph. Now let's take a look at the one below. The domain needs to be restricted to -pi over 2 to pi over 2, not including, with corresponding range of all reals. When that is done, the inverse is also a function and looks like what we have here. And the domain and ranges are reversed. But again, this is an analysis of the slope. What can you say about the slope of the inverse tangent function? Do you notice that the slope, that dy dx, is again always greater than 0, and on this case for all x, that's the Greek symbol for all x values, the slope is positive, the derivative is positive. The secant has to be restricted to 0 included to pi over 2 not included, with union of pi over 2 to pi. Now let's take a look at the secant function, the inverse secant function. Notice here again that it looks like the derivative is always positive, except possibly at these 2 points here. But other than that, we always have positive slope. The domain of the inverse secant is the range that I did not write over here, so the domain is going to be from -infinity to 1 in union with 1 to infinity. And the important part here is that the slope is always greater than 0 as long as we're between -infinity and 1, with union and 1 to infinity. What's happening at 1, -1? I'm sorry, this should be a -1. Okay, and so should this. Okay, so what's happening at -1 and +1? Well, it looks like those slopes are approaching positive infinity.